record on this computer. So, all right. So I'll start here. So I'm Wen Ming. I am the product manager on the AWS AI team. So I cover a few different products, including DGL. So we're very excited to bring you this user community. And I think we've been running this for about 1.5 years now. I know many of you have this, what's it called? Remote meeting fatigue by now, and our user group is still going strong. And I've seen the Slack channel grown from just 200 people, 300 people, now almost 1,300 people. So we're really excited, to work with this community. And of course, there's a lot more we can do. It's just that there's always, limited resources. And if you feel like you can help with the community, if you want to present, don't be shy. Let us know ahead of time, email us, or just directly Slack us on the channel. We'll be happy to have you present here. It's a great place for students and also people who are working for companies to practice their presentation as well. So I also see Joe here. So Joe is from NVIDIA, and also Grace from NVIDIA, that we have been working together essentially to bring this monthly meeting to the group here. So we're going to do exactly the same format today. And first of all, welcome. And it's already April. The year just went by very quickly. And hopefully, if you're looking at the recordings, also give us feedback, please. So I think we're going to be we're going to do a slightly light schedule. We're going to go over, I think, Yiwei from National University of Singapore, and he's currently in Seattle. He's going to give us an overview of his paper, Mixup for Node and Graph Classification, which is very interesting. And then Mingjie, who is on our Shanghai, who's a dev lead on the DGL and our Shanghai team. He's going to talk to us about DGL Go. Essentially, it's a CLI or command line interface for making training and applying GNNs much easier to do. And then we can have an open discussion to see, if you have any questions, feel free to ask them. So with that, I'll have Yiwei give a introduction of himself and then start with the presentation.
Yeah, so let me first share my screen. Yeah. So I guess that you can see my screen. Right, so I am Yiwei Wang, and I'm currently a final year PhD student in the National University of Singapore. And today I'm happy to be invited by the Dr. Xiang Song to make this presentation. In this presentation, I will introduce my paper, our paper titled Mixup for Node and Graph Classification. So let us start. Graph neural networks have achieved state-of-the-art performance on graph learning tasks, including node classification and graph classification. Graph neural networks are capable of making predictions based on complex graph structures, thanks to their advanced representational power. However, the increased representational capacity comes with higher model complexity, which can induce overfitting and weaken the generalization ability of graph neural networks. In this case, a trained graph neural network may capture random error or noise instead of the underlying data distribution, which is not what we expect. To combat the overfitting of neural networks, data augmentation has been demonstrated to be effective. Mixup is a recently proposed data augmentation method for image classification. Through linearly interpolating pixels of random image pairs and their training targets, Mixup generates synthetic images for training, just as shown in the left-hand side. For image classification, the existing Mixup generates synthetic images by interpolating both image pixels and labels. On the middle-hand side, we can see that for node classification, to mix a pair of nodes, for example, the A in red and B in blue, we need to mix their receptive field subgraphs. On the right-hand side, we can see that for graph classification, we need to mix the nodes and the graph topology of a pair of graphs. Although Mixup is effective in augmenting the image data, designing Mixup methods for graph learning is challenging. The challenges are rooted in the irregularity and the connectivity of graph data. Graph neural networks learn nodes representations via the message passing mechanism, which aggregates the representations between each node and its neighbors at each layer. As a result, the representation of a node relies on the nodes and edges inside its receptive field, all of which act as its features. Thus, to mix a pair of nodes, we need to mix their receptive field subgraphs, which consist of nodes and topology. However, unlike image pixels, nodes are not placed on a regular grid, but are instead unordered, which makes it difficult to pair the nodes in different subgraphs for mix-up. Besides, the interpolation is not well defined for graph topology, which is necessary for mix-up. Furthermore, due to the connectivity between nodes, the use of mix-up on different node pairs can interfere with one another, which can cause conflicts and perturb the mixed features. We interpolate a pair of nodes or graphs, as well as their ground truth labels, to produce a novel and a synthetic sample for training. To mix the graph topology, which is highly irregular, we propose the two-branch mix-up graph convolution. In principle, a graph neural network layer updates node i's representations by aggregating the representations of itself and its neighbors. By stacking L layers, graph neural networks make the final layer prediction of node I based on its L-hop neighborhood, which is known as node i's receptive field. In other words, to interpolate the paired nodes I and J, we need to mix their receptive field subgraphs. To achieve this, we propose the two-branch mix-up graph convolution, as shown in the right-hand side, where we mix the node attributes of node I and J before the input layer. Next, we conduct the graph convolutions based on node I and J's topologies separately at each layer, and mix the aggregated features from the two topologies together before the next layer. With our two-branch mix-up convolutions, here, how to compute the node i's neighbors representations is an issue. If we follow the same implementation as the classical mix-up, that is to say, we randomly pair the nodes in the mini batch to conduct mix-up and conduct the feed-forward for all the nodes synchronously, the conflicts can happen. An example is shown in this figure. On the left-hand side, we see that a graph neural network model predicts the class of node A in red by aggregating the nodes in orange inside node A's receptive field. On the right-hand side, we can see that to mix up node A in red and node B in blue, we should mix the features inside A and B's receptive fields. However, if we conduct the mix-up for node C in orange and node D in gray at the same time, the mixed input features from nodes A and B are perturbed by interference from node D through node C, which should be blocked. For node classification, graph neural networks learns the high-level semantic representations by stacking L layers and minimizing the classification loss, for example, the cross entropy over the final layer predictions as presented in the left-hand side. To resolve the conflicts between the mix-up on different node pairs, we propose the two-stage mix-up framework as shown on the right-hand side. In the first stage, we conduct the feed-forward to graph neural networks for the mini-batch graph to obtain the node's hidden representations without mix-up. Next, in the second stage, we randomly pair the nodes in the mini-batch to conduct the mix-up of node attributes. Then, we conduct our two-branch mix-up graph convolutions for the paired nodes. Note that at each layer in the second stage, we use the neighbors representations without mix-up, which are obtained from the first stage to conduct the graph convolutions. In this way, each node's representations after mix-up do not interfere with the message passing for other nodes. Sorry. With our two-stage framework, we effectively prevent the input features from being perturbed by the nodes outside the receptive fields. We mix the graph level representations for the mix-up on graph classification, which encodes both nodes attributes and graph topology. Graph neural networks utilize a readout function to summarize the node level embeddings into a graph embedding. Graph neural networks embed the complex and irregular graph structures into the embedding vectors of fixed dimension. We conduct a mix-up for graph classification in the embedding space, as shown in this figure. Finally, the interpolated graph level embedding will be passed to a multi-layer perceptron, followed by a softmax layer to produce the predicted distribution for the targeted classes. In this table, we present in our experiments, we present the performance of various graph neural network models trained with our mix-up methods. For node classification, we report the experimental results on both the transductive and inductive settings. For graph classification, we report the test accuracy on both chemical and social graphs. After that, we adjust the volume of labeled data to evaluate the generalization of graph neural networks with and without our mix-up. In addition, we visualize the learned representations of graph neural networks trained with mix-up compared with the graph neural networks without mix-up. Last but not least, we conduct ablation studies to show the sensitivity of graph neural networks performance with respect to the hyperparameters of our mix-up methods. For node classification, we use the standard benchmark datasets, Quora, Citizen, Pub, Flickr, Yelp, and Amazon for evaluation. The first three are citation networks, where each node is a document and each edge is a citation link. In Flickr, each node represents one image, and an edge is built between two images if they share some common properties. Each of them contains an unweighted irregularity matrix. The statistics of these datasets are summarized in this table. We use the standard benchmark datasets for the evaluation of graph classification. The first three are chemical datasets, where the nodes have categorical input features. The last three are social network. The statistics of these datasets are summarized in this table. We conduct the experiments under both transductive and inductive settings for a comprehensive evaluation. In the transductive setting, we have access to the attributes of all the nodes, but only the labels of nodes in the training set for training. In the inductive setting, both the attributes and labels of the nodes in the validation or testing set are unavailable during training. In the transductive node classification, the results are reported in this table. We observe that our two-stage mix-up method enhances graph convolutional network and JKNet to outperform all the baseline methods. In the inductive settings, the similar phenomenon is observed. For graph classification, we follow existing work to use the cross-validation scheme for a fair comparison and evaluation. Overall, Mixup achieves substantial improvements for graph convolutional network and GNN on both the chemical and the social datasets. As a result, Mixup enhances GCN and GNN to outperform all the baseline methods. Taking a closer look, we observe that the graph kernel methods generally present worse performance than the graph neural network methods. This demonstrates the stronger fitting capacity of the advanced neural network models. Mixup generally achieves high improvements on GNN than that on GCN. The reason is that GNN is a more advanced graph neural network model proposed for graph classification than GCN. However, the increased learning power of GNN comes with high risks of overfitting. Our Mixup method effectively regularizes them by interpolating the graph representations to expand the training set, which reduces the overfitting tendencies successfully. Please refer to our paper for more experimental results. Thank you for your time.
Yeah, thank you, Yiwei. And do we have any questions for him?
Yeah, hey, this is Tristan from NVIDIA. I do have one question for Wei. Do you think the Mixup, improve the accuracy by their certain level of regularization? Like, could you elaborate a little bit more, like why this Mixup, regularize the model and make the accuracy improved?
Okay, thank you. Thank you for your questions. So, so actually, originally, when the Mixup is proposed, it does not really be limited to the image data. It is actually limited to some regular data. I mean, some vectors or high-dimensional vectors, such as the tensor. So here, the image is actually just a special kind of the tensor, which holds three-dimensional, the width, the height, and also the channels. So here, its idea is that given this kind of vectors or the regular data, if we find some interpolated point in the input space, then accordingly, your prediction or the ground truth label should also be on the interpolated point. So for example, if we have 2 points in the input space, because you can just take the different data as high dimensional data points. If we have 2 points in the input space, then correspondingly on the prediction space or on the output space, if we find some point that is between, that is on the line between the 2 data points in the input space, then the corresponding prediction should be also on that point between the 2 outputs corresponding to the 2 data points. So to this extent, it is actually generating some new data between the space of different data points, not only between the data points in the same class, but also between the data points across different classes. And it enforces or regularizes, namely regularizes the models to make some interpolated predictions for this kind of generated data points. So in this sense, I think it is a kind of regularization. Thanks.
I think another good point you could make here, this is Joe, is this could help with robustness against attacks. One of the issues,
yeah, somehow if your attacks is working in some way that is similar to the interpolation across different instances, then I think it could help. So otherwise, if it is not some interpolation like the attacks, for example, it is some random erasing or cutout in the image community. I mean, some just remove some edges or remove some nodes. So in this sense, it may not work in a similar way of the mix-up. And maybe in this sense, some other delimitation methods could help to improve the robustness. Thanks.
Can you comment on the training time? Does this require more epochs to converge because of the regularization?
Yeah, sure. I observed the improvements on the number of epochs for the convergence, but not very largely. So generally, if you increases the original total number of epochs to some 2 times, then it is good enough. And at each epoch, the time complexity is not improved in theory, but be doubled. So it is multiplied by a constant, which is 2. Thanks.
I think there are also someone posted a question on the chat.
Okay, let me check it. Oh, so the first question is how to apply this our mix-up methods for the link prediction of negative sampling. So actually, I do not think this is just a simple question to name it as an application. Actually, the mix-up is generally defined to handle all kinds of the classification problem. So link prediction can be taken as a special kind of the binary classification problem between the node pairs. But to propose some, but to utilize the mix-up for the link prediction problems, it is not just as simple as applying our methods for the link prediction. We need to propose some new techniques, as I expect. Thanks. And the second question is that the isomorphism problem is deal with. So could you please well define namely the isomorphism problem? Thanks.
I do have a question just on, what kind of applications this could be useful for in terms, like specific tasks or problems that would be very interesting that you would imagine this could apply to.
Okay, so basically our method can be applied to any node classification task or the graph classification task. So just as introduced in our paper and also in some very famous public benchmarks such as Quora, Citizen, Public, and also the OGB datasets, which are very widely used nowadays. There are different cases. For example, we can predict the academic topic of one document of one paper, which is just a node in the graph. And maybe sometimes we can also classify the communities of different nodes. So here the nodes are users in some social network. And for the graph classification, there are also some kinds of tasks such as similar to it. So example, predicting the topics of the movies, and also predicting the functions and of the proteins. But recently I'm looking for some jobs. So as I know, in the industry, generally people use the node classification for the fraud detection, for the abusive prevention, and also for the community or some interesting finding. So this is my experience, personal experience. Thanks.
Okay, thank you. So I think, yeah, once again, thank you for the great presentation. And if you can just share your slides and in the Slack channel, that would be great.
Okay, no problem.
Yeah, thanks. And next we have.
Sorry,
go ahead.
Yeah, I just had a question.
Yeah.
How is the mix-up coefficient? Is it sampled from uniform?
You mean how do I sample the weights, the mix-up weights, or how do I sample the node pairs for the mix-up? Which one?
Both. But how do you?
Okay.
Yeah.
So basically, in terms of the first question on sampling the weights. So for example, here the example here is the 0.5, 0.5, but actually you can just sample any value between 0 and 1. So one distribution for the choice is just the uniform. So everywhere between 0 and 1 is the same probability. But if you use that distribution, you can get some good performance improvements. It is what I have observed. But you can also try some other options. So actually, in the original paper of the mix-up, people propose some other distributions, which is not the uniform distribution. So you can make the probability to be higher, around 0.5, or higher when it is close to the 0 or 1. So you have some options like that. So in my experiments, I found that if you set a distribution which holds some higher probability, around 0 or 1, the performance is generally better. But it is not some common sense knowledge. It is just depends on your performance on the validation set and test set. So this is the answer to the first question. The second question is how to decide the node pairs for the interpolation and for the mix-up. So actually, during the training at each step, you just sample some mini batch for the training. So if you follow some original graph convolutional pipeline, and also on some small data sets, which can feed the whole graph to the GPU, to the single GPU for some full batch training, then in this sense, your batch just includes all the nodes in the whole graph. So given this batch of the nodes, we just need to do some random shuffling. So random shuffling for the indexes, for the node indexes. So for example, from the index from 0 to the n-1, and here n is the number of nodes, you can just shuffle these indexes, and you can just take the node pairs between before the shuffling and after the shuffling, index by index. Then you just get n node pairs for the mix-up. So this is what we do in the paper.
And this is the final embedding readout.
Final embedding readout. What do you mean
by running through the L layers of your GNN?
Yeah, sure. Because here you have n pairs, so you just have n ground truth labels, and you just calculate the losses.
And just a final question: have you tried mixing intermediate layers?
Yeah. I haven't. I haven't.
Okay.
I also know there are some papers in that way, such as manifold mix-up, which is a follow-up work of the mix-up. And on the graph classification and node classification task, I haven't done that. I just consider the input features mix-up. But after this paper's publication, there has been around 1 year. So I guess that there should be some follow-up papers, maybe working on that way. Thanks.
Got it. Thank you.
Yeah, thanks.
So I have one quick question.
Yeah.
Do you have any insight or experimental results at which pair of nodes, like when you mix them up, produce the best result? you said that you are doing random selection, right?
Yeah.
But is it possible to further shrinking or zooming into some pair that is more important than the others?
Oh, okay. This is a good question. So basically, I do not analyze some phenomenon to separate different nodes into different groups to say which one is more beneficial and which is one is not beneficial. But I have thought this kind of problems in some of my other work, other publications. So basically, I think intuitively, if we want to know what pairs are more beneficial, we can analyze its training loss, or even though it is in the testing set, we can still calculate its loss. So if its loss is higher, then somehow it is more challenging for the model to get some good result. So in terms of this, we can think that it is more meaningful or beneficial, and this also is aligned well with the gradient-based optimization, because if your loss is higher, then correspondingly your gradient magnitude is higher. So it will influence the model parameters updating more heavily. Thanks.
I see. So yeah, because this is perhaps what the chat question means. Yeah. So the chat said, okay, isomorphism problem. I guess. I mean, it may because, like, for example, some of the two nodes, if they have the same class, right?
Yeah.
Their receptive field, the subgraph may be isomorphic. In such way, then the mix-up is like augmentation. It's like, okay, I emphasize the model to learn the same class. But it is also possible that some of the label, like the nodes, they belong to the same label.
Yeah.
But again, they are like near their neighborhood looks very similar. And this way, this makes the model difficult to classify. They need to find some other clues.
Yeah. I agree, because if you given some node pairs which is very close to each other, I mean, two nodes are very close to each other in the topology, or even just the one-hop neighbors for each other, and in this sense they belong to different classes. So based on the message parsing, and just as you know, the very well-known the over-smoothing phenomenon, it is very easy for the current message parsing-based graph neural network models to give the very similar predictions for them. But in this sense, if we can do some mix-up for them to generate some new sample based on the interpolation of these two connected nodes, then in this sense, we are enforcing the models to make some uniform distribution output between these two instances predictions. They actually will just enlarge the distance of these two data points outputs in the high dimensional embedding space. So this is my point of view. Thanks.
I see. Gotcha. Thanks.
I think
Tristan has another question.
Yeah. So let me first respond to this question given by the Mr. Tristan from the NVIDIA, and he asked how about mix-up for more nodes, mix the 4 nodes instead too. Yeah. So actually, we do not really need to limit us to just mix some node pairs. Actually, we can mix some group of nodes, and also we can do the interpolation for this group of nodes ground truth labels. It is fine. And also, as I know, there are some work in the in the image community and also in the natural language processing community, maybe working on that way. But for the graph community, I haven't tried it, and I believe that if nobody has tried it, it is a very good future direction. Thanks.
Okay, I think that's all the time we have. We'll next go to Mingjie. Mingjie is going to talk to us about DPL Go.
Okay, so let me share my screen. So actually, I have a different title with me, but anyway, that's okay. Like, so I'd like to talk about more things, more than DPL. DPL will be part of the presentation.
Yeah, no worries.
Yeah. So this presentation will about actually from January to April, the updates and also their highlights. So my name is Mingjie Wang. I'm from AWS Shanghai AI Lab, and I'm also the tech leader, the dev leader of the DGL team here. So when we look at these 2 months, actually this is a fruitful season. We have delivered a lot of things and many new updates. In March, we released the GL 0.8 with a lot of improvement on different aspects. For example, like sampling pipeline, heterogeneous GN, data augmentation, graph visualization. And as our old title, like suppose the title suggested, we also released a new tool called DGL Go, a command line interface for training and applying GNNs. And in April, just 1 month right afterwards, we released 0.1.8. That's a small release, but we include actually different modules for the latest research work. For example, reversible GM module, equivariant GN, which is very useful for cloud point data or like protein data, positional encoding, and principal neighbor aggregator, and also some other improvements. So here you can see there are many new updates, and maybe you are wondering, okay, how you guys choose this like improvement? Is there any like general methodology behind that for saying, okay, which direction you wanted to work from? So that's why I'd like to step back a little bit and talk about, for example, the GN system, how it looks like. So generally speaking, we can characterize a GN system, the API, the interface of it, from 2 dimensions. So the first dimension is functionality. So you can imagine as a GN system, we probably have a lot of different functions and APIs for them. For example, a core GN computation, which is quite important for like all the GN modules, like message passing, these utilities. Graph analytics, another important aspect of a graph neural network. Actually, if you look at the latest research work, you can see more and more people is infusing graph analytic algorithm with graph neural networks. Heterogeneous graph also quite a dominant data structure in the real world. Sampling, very important for scalability, data utilities, and the distributed training. So that's one dimension. The other dimension is API level. So this is where the customers are caring about. For example, in a very high level, we have like people who mostly working on data, like data scientists. They care about, okay, how to utilize the existing components to solve some specific business tasks on certain data set. And we also have machine learning researchers, engineers, and they were not only working on data, but also working on models. And one trend I found is many machine learning engineers or researchers right now are pretty good hackers, as they can actually not only touch the very upper level APIs, but also like working on like quite low level components like operators. And finally, we have people who care more about the low level system stuff, like system researchers, system engineers. Okay, so think about, okay, how to optimize the whole system, how to improve the system performance by utilizing some system tricks. So you can see there are actually 2 dimensions, and using these 2 dimensions, we can break down a GN system, their APIs, into a 2-dimensional space. For example, for high-level APIs, in terms of the core GN computation, we have model zoos, modules. Graph analytics, of course, we have like graph algorithms. These APIs should provide functionality like random walk, like shortest path, so on and so forth. And heterogeneous graph, of course, we have heterogeneous GM module, sampler, and data utilities like dataset and transforms are very important abstract for these levels. And for distributed training, of course, we have launcher and distributed sampler. In a medium level, I would say a medium level, there are more components below these like high level APIs. For example, tensor and sparse tensor, these are more like a lower level. If you think about like in PyTorch, we have other modules that is higher level, and the tensor is like in a more middle level, so lower levels than other module. And if we make this analogy to the GN system, you can see that the graph and heterogeneous graph is actually at a similar role. And also for GN, you have like a special operator, not only the regular tensor operator, sparse tensor operator, like a message passing operator. Similarly, in a mid level, you have like a data loader operator for graph sampling, and some data utilities, and also for distributed training, we have like graph server, feature server, these more lower level components. And in the very end, on the system level and infrastructure level, there are like CUDA kernels, CPU kernels, storage format, and also some network communication components for distributed training. So you can see there are actually a lot of components in a GNN system. And the hard lesson we learned is, as an open source system, open source framework, we don't have a distinguish between what are the user APIs, what are system APIs. Actually, all of these components are user-facing APIs. They just face different customers and different users. And when we evaluate how each component is designed, we need to evaluate both of them. We need to evaluate two metrics. One is whether they are easy to use. The other is whether they have high performance. So you can see this is why building a system, a framework, especially open source like deep learning framework, is so difficult, as all these components are exposed to the end users. Okay, so now we have essentially a map, right? Like you can think about a world map, and what are the new components we are delivering in the recent few months? So we can actually highlight them on this map. For example, the first one is the sampler part. We actually simplify the sampler interface and also optimize the data movement by a lot. So this is, you can see here, the improvement is from both usability and performance aspects. The other improvement is the heterogeneous graph models. So we actually provide a new operator to simplify the computation of heterogeneous graph neural network. And also the new operator improves the performance by more than 1 order of magnitude sometimes. And the next is the data set. Actually, this is quite important. And also, as our previous speaker mentioned, data augmentation has become a very important, actually, research topic in GNN research. So we actually greatly improve this data utilities in our recent releases. We provided new data augmentation transformation APIs and also support data set adaptation. Say, okay, if you have a data set originally designed for node classification, you can easily adapt it into for link prediction. So you can try out different data set on different tasks very easily. Another thing is for graph analytics. Recently we're actually working with Hong Kong University to release a new tool for visualizing and understanding graph data using GNN explanation model. So yeah, again, it's a usability update. Try to make like try to make GNN putting them into use for certain scenarios. And of course, very importantly, we have updates on core GNN computation of the APIs like model zoos and GNN module. So we add new GNN modules and a standard server model interface for different learning tasks. And of course, very importantly, we delivered a DGGO, a command line tool for training and applying GNNs. But beside that, we also have updates on other parts that I will not cover due to time limit. But you can see here, so we actually have touched a lot of parts, and this is why you can see there are actually a lot of updates, but they are actually organized in this whole spectrum. And for the rest of the part, we are also actively looking at it and see how can we improve that incrementally. So okay, next I will talk about some of the important features very briefly. First of all is the sampling update. So we know that mini batch sampling is very important for large scale for training large scale GNNs. And here is how it looks like, how its pipeline look like. So given a graph structure and some node features, right? Oh, it's supposed to be should be very large that you cannot fit on one GPU. So the first thing we will do is to actually for the graph structure, we extract some subgraphs. So we make it smaller. That means that we can actually fit in GPU. And also using these subgraphs, we perhaps wanted to do some transformation on it. Probably like adding some edges or remove some edges like data augmentation, or simply transform the graph structure into a computational graph to facilitate the follow-up training. Another important thing is after we extract the subgraph, we also need to extract the features. That is called feature fetching. So after we get both the subgraph and features, we feed them to a neural network, a graph neural network for training. So originally, the pipeline, if we split it into different stages, we will put the training on GPU while the rest of the sampling and the feature fetching stage is on CPU. And then you can imagine that since for a graph, the graph is sparse and interconnected. Once you have a node, it's very likely that after several rounds of neighborhood exploration, you will touch a lot of data. So that's why for this kind of pipeline setup, the data movement becomes actually a bottleneck between CPU and GPU. Okay, so what's new in 0.9? Actually, what we did is we reorganized the sampling pipeline and put them into different hardware, different hardware consideration. So first of all, we actually allow doing sampling and also feature fetching on GPU directly. So we put a lot of things on GPU. This makes the whole sampling pipeline faster. But this actually brings another issue because, as I mentioned, if you have a node and graph is interconnected, after several rounds of neighbor exploration, it is likely that it will touch a large part of the data. So there's a large part of the receptive field will be large, so it is difficult to fit that sample or fit some data into GPU. So to solve that, we actually utilize a technique called CUDA universal virtual addressing, UVA. So this is basically a special type of memory. It is physically in CPU, but visible to GPU. So basically, you can have a large memory chunk that is at the capacity of the CPU RAM, which is very large usually. And you can also launch GPU kernel for on that for computation to speed it up. So having this pipeline makes it easier to actually makes it more faster to do not only the subgraph extraction, but also like feature fetching as well. So as I said, as I mentioned before, like when we deliver a feature, we don't want to only say, okay, this is very fast. We also wanted to make sure that the usability is good. So in 0.8, if you wanted to enable this fancy new optimization, it's actually quite easy. It's only a few lines of code change. So you can see here is a demo code. Normally, we will first create a sampler. Here, the example here shows creating a multi-layer neighbor sampler and a data loader as an iteration over all these mini batches. So in 0.9, we actually add new arguments. You can use prefetch node features and prefetch labels in the sampler to specify which node features or which node labels to prefetch. And on the data loader, you can turn on this UVA optimization by setting just one flag. So make it so you can see here, like using this optimization is quite easy. And the result is also very promising. So we observed that when we training in a graph stage model, a two-layer graph stage model on OGBM paper 100 million, we observe actually a 4x speed up on that. And I want to thank all the partners and also all the contributors from NVIDIA and also from academia university like UIUC and the University of Edinburgh. They actually contribute, some of them, they actually working on very important like core coding part. And without you guys, we cannot have these features in 0.9. Okay, the other part that I wanted to highlight is heterogeneous GM module. So we observed that many SODA heterogeneous GM module actually involves such kind of computation. So you can see an equation here. So normally for a linear transformation, it is y equal to x multiplied w, where w is a matrix, is a weight matrix. But for a heterogeneous module, the w will have a subscript, that is the type. So you can see here, there's a tau x here. This tau is a mapping from the sample to its corresponding type. And what this equation means that whenever we do a linear transformation on heterogeneous module, I wanted to apply a linear transformation according to the sample's type. And we call it a type-specific weight matrix multiplication. And we found that actually many modules has this type of logic. So therefore, in the new release, we added a new operator called gather_mm, and we added a new operator called gather_mm for this certain kind of operation, and also a new module called typed linear that actually internally maintain the weight matrices. So you only need to provide an X and also corresponding type, you can get actually the final result. This new change not only perhaps I'll spoil it, not only actually makes the implementation much faster, sometimes an order of magnitude faster, compared with some of the baselines, both from DGL and PYG. We also shorten the RGC encoding implementation by 3x. This is a huge reduction. So originally it takes like 200 lines of code, and it is very convoluted. It is, we receive many users complaining that, okay, we cannot understand what RGC encode is doing. But right now it's very simple. You can see I can even fit the core part of it into one slide, like just several lines of code, and the core part, the part that you pay attention to is this typed linear module. So essentially, given some like dimension information, you have this linear, and you can just apply this linear on your data, and you get what the final output is. So here, this is again improvement from both usability and system optimization. But I also wanted to point out that heterogeneous writing and optimizing heterogeneous module is always difficult. We actually found the previously mentioned optimization chance during our previous research exploration. We developed a compiler called Graphiler for graph neural network, and which has been accepted by ML6 2022. And we actually extract some of the core technique like the type linear this operator into DGL, integrate that into DGL 0.8. But even with that, writing efficient heterogeneous module is still very challenging. Right now in DGL, there are two implementations. One implementation is we will iterate over the adjacency matrix or every relation, sending and then aggregating messages only along those nodes and edges. For example, on your right-hand side, you can see a heterogeneous graph. For the first implementation, we'll first, for example, sending messages along the right relation, and then send messages along the side relation. The other implementation is sending and aggregating all messages at once, so to achieve a better batching efficiency. But you need to operating each message with different weight matrices. So this is the focus on 0.8. So we provide this type linear for these purposes. But our result shows that we cannot say, okay, implementation 2 is always better than implementation 1. Actually, when we test the HGT, a heterogeneous graph transformer, as that's another very popular heterogeneous graph neural network, we try it using the new implementation, comparing it with the old one. And here you can see this is a speed up of the new implementation in 0.8 compared with the old one. For certain type of data set, especially for data sets that have many relations, it has a good performance. It is very fast. It has speed up over 0.7, our own implementation, and also PYG. So you can see there's a lot of speed up. But when it comes to some other data sets, it actually has a performance regression. You can see this is a very difficult problem to solve. Right now, there's no one-for-all solution yet. Okay, this is for heterogeneous module. Of course, we added a bunch of new GM modules, regular GM modules to DGL in the recent releases. I just wanted to highlight one. There are a lot of them. You can check out our release notes or check out our documentation page. So this one has a very eye-catching title. It's called Training Graph Neural Networks 1,000 Layers. And it is actually one step on very deep graph neural network, I would say. So the core idea behind it is that since if you have a lot of layers, like 1,000 layers, the memory consumption will be huge. So it is likely that your model cannot fit in one GPU. So the author's idea is to design this reversible graph convolution layer, meaning that since it's reversible, so you don't need to record the forward activation, and you can directly compute the gradient on the fly. So this makes the whole model computation very lightweight in terms of memory consumption. So in DGL, a new release, we actually include that module. Here is a code snippet to show how to use that. So here you can see we can define an arbitrary GN layer. This layer contains one graph convolution, one batch norm, and one dropout. And you also define the forward function. And then you can just use this new DGL.n.graph regularizes. It's an awkward name, but it means that it is a wrapper module. After wrapping your own graph neural network layer, it produces a reversible convolution and also some group convolution and also residual connection. So that reversible convolution has is reversible, of course, is reversible. So when doing forward and backward, you can it use much less memory than the normal graph convolution layer. So this is for GN module. The other part, data augmentation, as our previous speaker has introduced very nicely. So data augmentation has been a very important research topic because I think this all starts from one paper called How Powerful Are Graph Networks. The paper said that, okay, if you are using like message parsing framework, it has a theoretical capability upper bound. So it cannot, for example, figure out some of the isomorphic of the graph. It cannot like distinguish them. So there are a bunch of new papers out saying that, okay, how can I use like add some data or augment some data to increase the expressiveness power of a graph neural network? And one important direction on it is to develop this positional encoding. So positional encoding is like, okay, say given a graph, I want to assign encoding. Encoding is like a high dimensional vector for each node in this graph. And hopefully that high dimensional encoding embedding can distinguish nodes of different neighborhood topology. So here is one example called the random walk positional encoding. So the idea is that for each node, I will calculate the landing probability of landing probability on that node when I do like random walk of length 1, 2, 3 to up to k. So here is an example on a synthetic graph. You can see these two graphs, they are not isomorphic. So all the embeddings, random walk embeddings, they have different value. And also for nodes that have locally, like I would say isomorphic neighborhood, they actually have the same random walk positional encoding. And this is for synthetic graph on the right-hand side. You can also see a real data set that is a zinc module from it is a molecule. And you can see for real world graph, it also has a very good, nice property that for those nodes that has the same have the same encoding, while for the others they are different. So this makes potentially makes the graph neural net easier to distinguish them. In DGL, we actually brought that into the core package as a type of data transform. This follows the PyTorch design. So here you can see whenever you use a DL data set, like a choreograph data set, right? It only has one graph. Usually you use graph embeddings on like positional encoding on data set of multiple graphs, but you can also use that for single graph data set. So you provide this like random walk P, short for random walk positional encoding as a transform to this choreograph data set. And after you fetch the data from the data set, from the graph from the data set, you can get the positional encoding directly. So it is already augmented. Okay, so that is data augmentation. And I would like to talk about one more thing. As a DGL, like the community growing, see many new users coming and asking about questions. For example, I've heard about GNNs, how to start training a GNN data set. I want to learn more about GNNs, how to start experimenting with all of these models. Perhaps this is like a researcher. I'd like to try out, but a new researcher try out some new baselines. And I have some new research ideas on how to start building it upon existing GM modules. So all these questions let us think about the process process of how a new user come on board, how they learn about GNNs, how they use a new framework. So we categorize the new user experience as following. So whenever we look at a graph neural network, we will first pick a task, for example, node classification, like pick a data set like Cora, pick a model like GN, and then I will try to train it. I train the model with the setup and to see the result. And to understand, okay, how the model works, we usually will, for example, inspect the code to understand how different pieces are connected with each other. And also do some tweaking on the configuration, like, okay, I will use a different node, different data set, for example, or like tweak the number of layers of that model to see how it influences the final output. So we would call this a learning phase because we will probably iterate over these like for several rounds to fully understand how this model works. And then, depending on what you are working on, we will try to put this into practice. So for data scientists, we'll try this model on custom data. For ML researchers, we'll invent new model upon existing ones. So we call this practice phase. Now we are graduated from the learning phase. We try to solve some real world tasks. So we want to make this onboarding experience extremely smooth. So our solution is called DGL Go. It is a command line interface for new GN users. Right now, you can just pip install DGL Go, you will find that, okay, it appears in your local repository. So after you install DGL Go, what you immediately get is basically a command called DGL. So it's kind of like process making DGL not only a noun, but also a verb. So for first of all, we have these two like commands. One is called DGL configure. So configure is a command that helps you to do these selections. Like you can specify the data set like Cora, the model, and also for task, you pick the pipeline. The pipeline, there's no prediction, and it will essentially generate a configuration file, in YAML for you. And you can tweak this YAML file based on your own need. And we also provide several, we call the recipes, which are the configuration files that we have verified its model accuracy. So for example, you can use DGL recipe, this command, subcommand, to get some of the recipes like that has been verified that is correctly. And after we have this configuration file, you can use DGL train with the configuration file as an input to train the model, with the setup. And for data scientists, of course, you might want to work on some custom data. So we provide a custom data interface to DGL train. You can actually use your data stored in CSV format. And most importantly, if this is the only thing we need to deliver, this becomes an experimental runner, right? So for ML researchers, we know that many of you guys need to want to have more flexibility, want to look at what's under the hood. So that's why we actually provide a third command called DGL export, which from the configuration file will generate a self-contained and a reproducible Python script that you can download to get the result. So here is a brief preview of what the generated Python script will look like. You can see here after you run all these commands called DGL export, you will get like a Python script like this. So this essentially makes DGL Go not only a command line tool, it also a code generator that generate a Python script for you. And because of the we bridge the gap of them, this makes it extremely easy for user if you don't have any coding experience or less coding experience as normal researchers, but you still wanted to start with some example code, and maybe your task or your setting is not available in the official example, you can use this tool to generate a custom piece for you. And actually, using this tool, we can also do something even fancier. So I will show you guys a demo. So here you can see this is a website. That's something we are working on. We haven't released that yet, so it's the first time you guys see it. Here you can see this is on your right hand side, there's a panel. This is essentially the YAML configuration file, but we pass it and display it on your right hand side panel, the selection. So you can see here, I can select a different pipeline, node prediction neighbor sampling, link prediction. I can also select what are the data set you use and what are the models you wanted to use. In the middle, this is essentially code that is generated by different selections. For example, here you can see this is a GCM model on Quora, right? So if I wanted to say, okay, I wanted to try out not Quora, but PubMed, right? So it will run in the behind, you can see this into PubMed graph dataset. Of course, I can change another model, like say graph state. Now it becomes graph state, and you can see all the code out there. You can look at, okay, how it is implemented, and probably you can also change that based on your own needs. And we also provide different pipelines, which has the implementation of the training logic. You can see here, this is a training code. Like you can see here is a loop over different epoch. I can choose, say, neighbor sampling, right? This is more advanced one. Neighbor sampling, and again, this becomes a new one. And you can see I created a sampler, a loader, and again, the one loop becomes two loops. One is for epoch, one is for the mini batches. And you can, after you tweak all these configurations, you can actually download the script or even just copy it here, copy it here. And the nice thing about this script that it's self-contained. It only imports libraries from a Visual DGL and for your PyTorch and NumPy. So you can, meaning that this script is portable. You can copy paste it to whatever you want, and you can run it, and it should produce the results that is expected. Okay, so this actually completes my my presentation. So I'd like to share some of the items on our next agenda. Of course, first of all, we want to keep lowering the entry barrier for new users. DGL is one step, but we also wanted to see how can we make the core APIs more usable. And the second very important mission is to make the training of large-scale GNNs accessible by everyone. Like we can see that right now the academic data set is growing larger and larger. And but training on this large data set is still quite ad hoc, difficult. So we want to provide these utilities for users to make it extremely easy. Of course, DGL Go, you can check out the DGL Go. It is currently hosted in DGL main repository. And we want to add in more support to it. For example, like graph prediction pipeline, model inference, and custom model architecture. And that's all I want to share. I'd like to take any questions. Okay.
Angie, this is Joe. So are there limits on the size of a model you could do with DGL Go? Does it support just DGL, for example?
You mean the size of the model or like the graph?
Yeah, I mean the graph actually. Yeah, that's what I mean.
Yeah. So right now, all this depends on pipeline, of course, right? For this node prediction and link prediction, these are using full graph training methodology. So that means the graph data need to be fit into the entire graph data need to fit into GPU. While for neighbor sampling is like storing all the data on CPU and doing feature and subgraph extraction, put that into GPU. So we can fit data that is as large as CPU RAM. And I think the one thing we are planning for is to bring up more like sampling method, sampling-based training pipeline into DGL Go. And also perhaps in the future, we can have multi-GPU training pipeline set up as well. So to make it train faster as well as bigger graph. And perhaps the eventual ultimate goal is to have like distributed training to make it like over one command, you can train on a training level graph easily without considering all these details.
Yeah, thank you. That's exactly what I was thinking also was we'd kind of want to build up a set of modules for different training regimes, right? So single GPU, multi-GPU, distributed, for example. Yeah.
Yeah.
Yeah, I would also encourage folks to give it a try, and certainly would be good to have folks give feedback and see if it's able to work on the task that you want to accomplish. Any other questions from Mingye? No? Great. So this is recorded. So I have this recorded, and I'll upload it as soon as my laptop finishes processing it. And well, I wish everyone a great rest of the April and a great May. And we'll see everyone on the 26th, I believe, 26th of May. I think we already got one presenter ready to go, and I'm certainly looking for another one. So feel free to reach out to me on Slack, and we'll be happy to add you to the presentation next month. With that, anyone else would like to share anything before we disconnect? Okay, great. Well, have a great evening or morning wherever you are. Thanks. Bye.
Thank you.
Thanks.
Bye.
Chris. Bye.
Bye.
Bye, everyone. Thank you.